Good evening, everyone. Thank you very much for joining us tonight as we are proud to present Dr. Adam Hincks and his star talk, How to Measure the Universe's Oldest Light and What It Tells Us. ASX is very proud to have Dr. Hincks here today. He is the inaugural holder of the Sutton Family Chair in Science, Christianity and Cultures at U of T's David A. Dunlap Department of Astronomy and Astrophysics, as well as at St. Michael's College. Professor Hincks is an ordained Jesuit priest and is affiliated with the Vatican Observatory. His main research focus is on cosmology. So without further ado, thank you very much, Dr. Hincks.
Thank you so much, Spencer, and thank you to Julie and Dwayne for organizing this talk. I'm really happy to be invited to it. I went back and looked at the history of the Astronomy and Space Exploration Society and discovered that it was founded in 2003, which was the year before I graduated, got my undergrad at U of T. But unfortunately didn't hear about you back then. So I'm really delighted to have finally discovered you. So thanks once again. I'm going to be talking about the oldest light in the universe, what it is, what it tells us, and how we measure it. So the oldest light is called the cosmic microwave background, which I'll often abbreviate as CMB. And during the course of this talk, I'll explain why it's called that, why it's cosmic, why it's microwave, and why it's background. And I'll spend about the first half of the talk describing the CMB, trying to get across the basic concepts. And then in the second part of the talk, I'll describe a couple of telescopes that are designed specifically for looking at this oldest light. The Atacama Cosmology Telescope, or ACT, and the Simons Observatory. Sometimes I'll call that SO. ACT is currently observing and SO is under construction. So I think when most people think about astronomy, they imagine an image like this, which was publicly available online and I pulled off and put here. This is the night sky that we're familiar with, at least if we go into the country. And as you probably know, the light that's coming from these stars is quite old. The distance that light travels in a year is a light year. Light travels at about 300,000 kilometers per second. And the stars we're seeing here are tens or hundreds, thousands, perhaps tens of thousands of light years away. And so we're seeing these stars as they were when their light was emitted, however many years ago, perhaps some of these before human beings even existed. But as far as I'm concerned as a cosmologist, this light is pretty young. If you want the oldest light in the universe, you can't look in optical wavelengths. You can't look using visible light that our eyes can see. You've probably heard of the different types of light there are. And I'm going to be going over different parts of this diagram over the next few slides. But this shows you the different wavelengths of light that exist and what they're called. Can you see my cursor, by the way? I'm going to, oh, good, yes, thank you. So visible light, the light that our eyes can sense, falls here. The wavelength of that light is less than 1/1,000,000th of a meter long. But at other wavelengths, ultraviolet or X-ray, which have shorter wavelengths, or infrared, microwave, radio have longer wavelengths, our eyes simply aren't sensitive to those, but that doesn't stop us from doing astronomy with them. And in this talk, I'm going to be focusing on microwave light, and that's where the microwave part comes from in cosmic microwave background. So I just showed you a picture of what the sky looks like in visible light, and now I'm going to show you roughly what the sky looks like in microwave light at these longer wavelengths. So there it is. What I'm plotting here is the whole sky, and you'll see that it's the same temperature everywhere, the same brightness. And I'm going to show a number of these oval maps in this talk. And when I show them, what I'm doing is I'm taking the spherical sky that's around us and projecting it on a flat surface, just like you can take the surface of the Earth, which is a sphere, and project it onto a flat piece of paper in an atlas. There'll be more interesting versions of this, but the point here is that unlike in visible wavelengths, where you see lots of different things, first of all, there's no light in a lot of spaces. You have a lot of empty spaces. And then you have pinpricks of light, whether it be from stars or galaxies or planets or these days even comets. When you look at the microwave sky, it looks radically different. Okay? And this fact was only discovered back in the 1960s by Penzias and Wilson using this radio telescope, which was state of the art in the day. It was originally made for communications, but they started using it to explore astronomy. And they found that no matter where they pointed this telescope at the sky, that they saw the same brightness everywhere in microwaves. They were looking at wavelengths of around 7 centimeter. And at first they thought that they were seeing an anomaly, that it was some kind of problem with the instrument. And in fact, they discovered that pigeons had been roosting inside of this telescope, and they found pigeon droppings everywhere. So they thought maybe that was creating a false signal, and they went in and cleaned up all the pigeon droppings. And then when they put the telescope back on the sky, they still found this uniform brightness wherever they looked. And they became more and more convinced that what they were seeing was a true background. And that's where the background in cosmic microwave background comes from. They're seeing a uniform light that's like a backdrop that you can see everywhere you look on the sky. And they didn't know at first what they were seeing. So they called some of their colleagues at Princeton University. This telescope was in New Jersey, so Princeton University was nearby. And the professors at Princeton, particularly a professor named Dickey, realized that what they were seeing was probably cosmic in origin. And let me describe that in a second, but first, in the advertisement for this talk, it was mentioned that when you see static on your television, you're seeing this microwave background. And that's true. About 1% of the signal that goes into the static on an old analog television is actually coming from space. It's the same signal that they were seeing. So what were they seeing exactly, and what are we seeing with the CMB? Well, here's a diagram of the history of the universe in one slide. I'm sure everyone has heard that the universe began with a Big Bang in an extremely hot and dense state. If I can borrow a phrase from the television show introduction. And it's been expanding ever since. Early on, there wouldn't have been any stars or galaxies. We think the first stars started forming a few million years after the Big Bang. But in the first few 100,000 years after the Big Bang, space was filled with a hot and dense gas of hydrogen and helium. And it was pretty much a uniform density everywhere. And hot things always glow. And so the physicists at Princeton knew that if the universe had begun in a Big Bang, it would be possible perhaps to see that glow, to see the glow of that hot gas at the very beginning of the universe. And this was something that people had suggested, but up until this point, the Big Bang theory wasn't widely or universally accepted. And so when they heard that they had finally seen this uniform glow over the whole sky, they realized that what they were probably seeing was a truly cosmic signal, looking at the light from the very beginning of the universe, or at least about 400,000 years after the Big Bang, which is very little time compared to the total age of the universe, which is almost 14 billion years. So what we see with the CMB is we're seeing this hot gas of hydrogen and helium, which is glowing, and this light has been traveling for almost 14 billion years, all the way through the universe to us today. Okay. So this is one of only two graphs that I'm going to show in this talk, but this shows you how different temperatures emit light. So you probably know that if you stick an iron in a fire, it first starts glowing red, and then as it gets hotter, the color changes. It becomes white and then blue. That's because the color or the wavelength of light that something emits depends upon its temperature. So our sun, the surface of our sun is about 5,000 degrees Kelvin, which is roughly 5,000 degrees Celsius. And an object that's 5,000 degrees emits most of its light in the visible part of the spectrum. Right? And that's why we see visible light. Most of the light emitted by the sun is visible, so our eyes have evolved to be most sensitive to that light because most of it is in this wavelength. And as you have cooler objects, you can see that the wavelength gets longer. So I should have told you what's plotted here. What's plotted on the y-axis is the amount of light, basically, and on the x-axis is wavelength. So these are longer wavelengths, and shown here are the wavelengths that the human eye is sensitive to. So you can see if you have a cooler object, say 3000 degrees, it still emits some visible light, but now most of the light that it's emitting is in the infrared. And as you go to cooler and cooler temperatures, the wavelength gets longer and longer. So the human body, for example, we all have a temperature. We're all about 37 degrees centigrade. We don't emit visible light, but we do emit infrared light. And that's how night vision goggles work. They're using infrared light, and therefore you see things like human bodies that are glowing at those frequencies. Now, this CMB, this light coming from 400,000 years after the Big Bang, the gas was several thousand degrees Kelvin. It was about 3,000 degrees. So if you were able to travel back in time, and you were able to survive in these hot temperatures, you would actually be able to see this light with which the early universe was glowing. You'd see a very intense, bright light coming from this gas, because it would be similar in temperature to a star. But we see it in microwave frequencies. Well, why is that? Well, the universe is expanding, and this diagram doesn't show it very well, but between here, 400,000 years after the Big Bang, and today, the universe has actually expanded more than 1,000 times. So it's gotten about 1,000 times bigger. And all the light inside has been stretched. Its wavelengths have been stretched so that they're more than 1,000 times longer. Or another way of thinking about this is that as the universe expands, it's as though this early universe, this hot gas in the early universe, it's as though it's moving away from us extremely rapidly. And that causes the light, that causes the wavelength of the light to stretch. And the technical word for that is redshift. And so when an object is moving away from you, the wavelengths get stretched out and the light becomes redder, the wavelength becomes longer. And the opposite of redshift is blue shift. If an object is moving towards you, the wavelengths get compressed and the light gets bluer. And you may have heard of the Doppler effect that happens with sound. It's the same kind of phenomenon. If an ambulance is passing by you, you'll hear a lower pitched siren, and then as it passes by, you'll hear the pitch increase. So you hear something that goes like, ooh, 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 or the other way around. It will go, ooh, ooh, ooh. And that's because when the ambulance is traveling away from you, the wavelengths get stretched out. And the same thing happens with light. Right? So the light that was emitted from this gas that was 3,000 degrees Kelvin has been redshifted by about a factor of 1,000, so that today it's as though the temperature was 1,000 times less, or about 3 degrees Kelvin, 3 degrees above absolute zero, which in centigrade is about minus 270 degrees. So the cosmic microwave background looks like a very cold object today, and therefore it's in the microwave part of the spectrum. So now let me show you a little bit more of this diagram here. This shows you how well different frequencies penetrate the Earth's atmosphere. And this turns out to be a problem for observing this cosmic microwave background. Visible light very easily passes through the atmosphere of Earth. And that's obvious because we can look up and we can see the stars, we can see things with visible light. But at other frequencies, the atmosphere actually blocks light. So for instance, X-rays can't penetrate the Earth's atmosphere. They collide with the atmosphere and they don't get through down to the surface of the Earth. So if you want to observe very short wavelengths like X-rays or gamma rays, you need to go into space to see them. Similarly, ultraviolet light, at least a lot of it is supposed to be blocked by the ozone layer. But as we know, if the ozone layer gets thinner, some of it comes down to Earth, and that's why you get sunburned. Now, if we move to longer wavelengths, to microwaves, which are here, unfortunately, a lot of microwaves also get absorbed by the atmosphere of the Earth. And the reason is very similar to why a microwave oven works. So a microwave oven is called a microwave because it uses microwave light to heat your food. And the way it does that is by heating up the water in your food. Water molecules very efficiently absorb microwave light. What it does is it tends to cause the molecules of water to start spinning. And that heats up the water, which in turn heats up your food. So basically you're shining microwave light on your leftovers. That causes the water molecules to rotate when they absorb the microwave light and your food heats up. And a very similar thing happens in the atmosphere of the Earth. There's lots of water vapor in the atmosphere, and that water vapor absorbs the microwave light that's coming from space. And so a lot of it doesn't reach the surface of the Earth. So if you want to see this microwave background, a little bit of it does get through to the Earth. That's how Penzias and Wilson saw it back in the 1960s. But really, if you want to see it well, you need to think very carefully about where you're going to observe from. So the best place, obviously, is to observe from space. And this NASA satellite called COBE, that I'll talk about soon, was a space telescope. Another way you can do it is with a balloon telescope. So there are some research groups that build telescopes that you can hang from the bottom of a helium balloon. And you go to the Antarctic and the balloon floats up about 50 or 60 kilometers above the surface of the Earth to the point where it's almost in space. So that's another way that you can look at the microwave background. I'll show some more pictures of balloons later. But what I'm going to be focusing on are the measurements you do from the ground. And if you want to observe this microwave background from the ground, you really have to find a location that's at a high altitude and that's very dry, so that you have less atmosphere and so that there's very little water vapor in the atmosphere. And so that's what I'll be talking about in the second part of this talk. But let me start by telling you a little bit about what this COBE instrument did back in the 1990s. It released its results in 1994, and 3 of the lead scientists won the Nobel Prize for this work in 2006. One really cool thing that COBE did was to measure this spectrum of light that's coming from the microwave background. So what this plot is, this is basically plotting the same thing that I was showing here, this curve that shows you how much light is emitted as a function of wavelength. And for those of you on the call that have studied a little bit of physics or physics majors, this is a black body curve. This is the spectrum of light that's emitted by an object that's almost perfectly smooth. Close parentheses on the technical jargon. The green line here is the theoretical prediction. And the red crosses are the measurements that this COBE satellite made. And there are actually tiny little error bars indicating the uncertainty of each of these measurements, but they're so small that you can't really see them in the way this is plotted. And you see that the red points fall exactly on what was predicted. And this was kind of the final proof that this cosmic microwave background really is coming from the early universe, because really the only thing that anyone could think of that could produce this spectrum is the hot gas, is this almost perfectly smooth gas of hydrogen and helium that's very hot at the beginning of the universe. The other thing COBE did, in addition to measuring this spectrum, was to make a map of the whole sky. So remember that the intensity or the temperature is almost exactly the same everywhere. And they measured this temperature. It's 2.72548 degrees Kelvin. They measured it to about 5 decimal places. But what they did was they were able to see very small variations in that temperature, and they made a map of it. So this is the map they made of the tiny variations in temperature from place to place on the sky. So it's almost exactly 2.7 degrees Kelvin everywhere, but the temperature has tiny fluctuations that are about 1 part in 100,000. So 100,000th of a degree. And these correspond to tiny variations in density in this hydrogen and helium gas in the early universe. And what this is a picture of is sound waves in that gas. Just as in water, you can have sound waves. Um, you can perhaps hear an ambulance in the background to illustrate the Doppler effect, but it's passing by. But in the gas in the early universe, it also had sound waves, just like I'm making sound waves in this room right now. The air in this room is an almost perfectly uniform density everywhere in the room, but as I'm speaking, I'm creating small density variations. That's what sound waves are, that are going into the microwave, or going into the microphone that you're listening to. And almost exactly the same thing was happening in this gas of hydrogen and helium in the early universe. There were sound waves traveling everywhere, and that's what we're seeing a picture of. Okay, so that's really neat. We're really looking at the very fundamental conditions that existed in the very early universe. And why these sound waves are so important is that these are the seeds of cosmic structure. Remember earlier I said that the first stars and galaxies form a few 100 million years after the Big Bang. These galaxies and stars form where gas has clumped together and has become dense enough that stars can start forming, that nuclear reactions can start happening. The gas collapses because of gravity. So wherever the gas was a little bit more dense, that would be a center of collapse where gravity would pull things together. And so what we're seeing here is where those original centers would have been, where the slight overdensities that grew in time as gravity brought things closer and close together. These are the sites where structure later grew. So we're seeing kind of the initial conditions. We're seeing the seeds of what later grew into the structure that's around us today. Galaxies, stars grouped into galaxies, and galaxies grouped into clusters of galaxies. Okay. What's also very interesting about this microwave background is that the pattern of these fluctuations, by the way, the technical name is anisotropy. That's just the technical name for the variations in temperature, in these maps. And the sound waves, the precise shape of these waves, precise pattern, depends on the nature of that gas. It depends on how dense it is. It depends on what the speed of sound is. So it depends on all the physical conditions early in the universe. And it turns out that by looking at the precise details of the pattern, we can determine some pretty fundamental things about our universe. We can figure out how old the universe is. We can figure out whether its geometry is flat or whether space is curved overall. We can figure out what it's made of, and I'll be speaking about this in a little while. We can even infer things like when the first stars would have formed, all by studying these patterns. And I'll be saying a little bit more about all of these things later on. The trouble with the COBE satellite back in the 90s, however, was that it didn't have high enough resolution. It didn't have a very sharp image of the microwave background. So it's as though you're trying to look at the details of the waves, but you have a very blurry image and you can't see any of the features in what you're interested in studying. So after the 1990s, different experimental groups created telescopes that were sharper, that had higher resolution, to start looking at the shape of these sound waves in the early universe. So one example from the early 2000s was the Boomerang telescope. This was a balloon-borne telescope, and it released results in the year 2000. And Boomerang just observed a small portion of the sky. And this is the map that they made of the microwave background. So now you can see this is a lot sharper. One of the reasons I mentioned Boomerang is that a couple people here in Toronto, Bart Netterfield and Dick Bond, were part of this team. Then a few years later, NASA launched another satellite called WMAP. And WMAP was really groundbreaking because it made a map of these temperature fluctuations over the whole sky. And you can see how much sharper this image is compared to COBE, which was almost 10 years previous. And then most recently, the most recent satellite data we have is from a European and NASA satellite called Planck, which released its first results in 2013, which is shown here. And it just finished a couple of years ago, its mission. And you can see here, if I switch between WMAP and Planck, you can see, first of all, you can see that a lot of the structure is the same. If you look here, it's warmer, for instance, but you're just seeing much higher resolution with Planck. And so Planck has these amazing results. And one really cool thing that they were able to do was to actually look at what the average shape of one of those sound waves from the early universe was. What we're seeing here is kind of the interference pattern of a whole bunch of sound waves. Earlier, let me go back. So if you think of raindrops falling in a puddle, each raindrop creates kind of a circular pattern of waves going out. But if you have lots of raindrops, all the waves start mingling together and interfering, and you get a very complex pattern. We're seeing something very similar in these maps. But what you can do is kind of reconstruct what a single wave looks like by taking all the hot spots in this map and adding them all up. And if you do that, you can kind of reconstruct what the average wave looked like. And this is a measurement. This isn't a theory or simulation. This is actually measured from this map. And this is what the average sound wave looked like in the early universe. And what's really cool is that we know how big these sound waves are because we understand the gas, we understand hydrogen and helium gas, so we can calculate things about how fast waves travel, and we can figure out physically how big these patterns should be. And we can use that knowledge to figure out how far away this light is coming from using trigonometry. Now, this is kind of simplifying things here, but what Planck did was they measured how big this angular size was, how big it is on the sky. You can calculate what the physical size is, and then you do a little bit of trigonometry. And it's a little bit more complicated than this little diagram, which is just a cartoon. But the basic idea is you measure the angle, you know this size here, and then you can measure the distance from us to this gas that we're measuring in the early universe. And that's how we use the CMB to figure out how old the universe is. Because we know the speed of light, we calculate the distance, and that gives you an age. And so one of the things that Planck has measured with high precision is the age of the universe, 13.7971 billion years. And these are a number of other parameters, another number of other numbers about the universe that Planck has measured. And I won't describe these symbols and these numbers. It's just to give you a sense of that they're measuring things to high precision. But another thing that's in these numbers is what the universe is made out of. So by looking at the precise shape of these sound waves, you can actually determine what the composition of the universe is overall, which I'll describe here for a second. So let's just concentrate on the left-hand pie chart here. And what this is saying, so the 5% here, 4% shown here, plus this white sliver here, 5% of the universe is made up of the kind of matter that we're familiar with, atomic matter, matter that's made up of protons and electrons and atoms and molecules and so on. But as we found with the CMB, and this can be confirmed using other astronomical measurements that I won't get into, but many of the most precise measurements we have are from the CMB. About a quarter of the universe is made up of what we call dark matter. And this matter isn't made up of the atoms that we know about, the atoms from the periodic table that you saw hanging in your chemistry classroom. But it's made up of some other substance. We don't know exactly what it is, but we know it's there because we can very clearly see its gravitational effect. Right? So about 1/6 of the matter in the universe is made up of atomic matter, and 5/6 are made up of this dark matter that we don't really know much about. And then, even more interestingly, about 70% of the universe is made up of what's called dark energy. And this is even more mysterious. In this, I'm going to go back to this diagram here. Um, we've learned that over the last few billion years, the universe has started speeding up in its expansion. So gravity tends to pull things together. So one would expect that as the universe expanded, it would be slowing down. But in fact, we've discovered the opposite. The universe is expanding and it's speeding up. Um, and we don't really know what's causing that. What we do know, though, is that there's some kind of energy field that permeates all of space that accounts for about 70% of the composition of the universe that's pushing everything apart. Right? So we know it's there, but we don't know what it is. So what's really remarkable is that 95% of the universe is made up of stuff that we really don't understand. So this is what you can see in the CMB. You can basically make this pie chart. And these numbers are a little bit out of date, but I liked the way this was presented. So about 70% dark energy, about a quarter dark matter, and then 5% the type of matter that you and I are familiar with. And then what's showing here on the right is kind of this ordinary matter. Now 4% is simply hydrogen and helium that's just in gas in space. It's not in stars, it's not in planets, it's just gas floating out there. And then 1% is, the remaining 1% is shown in this pie chart here. So 0.5% is in stars, 0.3% is in neutrinos. Neutrinos are very light particles that are produced by nuclear reactions. They're produced in the sun, for instance. And then 0.03% of the universe is made up of heavy elements, oxygen, carbon, nitrogen. Most of the things on planet Earth, most of planet Earth itself is made up of heavy elements. The stuff that we're most familiar with, apart from hydrogen in the water in our bodies, the rest of our bodies are made up of heavy elements. But in terms of the total composition of the universe, it's a very, very small fraction. All right, so we've learned an amazing amount from experiments like the Planck satellite. We've got detailed information on things like the age of the universe. We can measure precisely the composition of the universe. What else can we do by looking at this microwave background? Why have we built other telescopes like the Atacama Cosmology Telescope or like the Simons Observatory? Well, there are other things that we can study beyond the cosmological parameters that I've shown. And I'm going to be talking about some of the things in this list as I continue. But what we really want to do more science with the CMB is we want bigger telescopes. With bigger telescopes, you can get higher resolution, you can get sharper images, and the size of your telescope translates directly to the resolution that you can see with, the sharpness of the image you can make. And the bigger your telescope is, the more sensitive a camera you can put in it. Right? And the problem with going into space is that it just isn't feasible to start putting big telescopes in space, the size that we want to see some of these other things that I'm going to be talking about. So really, to extract kind of the maximal science from the microwave background, we're kind of forced to observe from the ground. And that's why we built the Atacama Cosmology Telescope that I'm going to start speaking about now. So I'll spend the rest of the talk talking about this telescope, the Atacama Cosmology Telescope. And at the end, I'll introduce kind of the next generation instrument, the Simons Observatory. So here's a picture of ACT here. A number of universities and research labs from different countries in the world, including here at U of T, are involved. Logos shown down here. ACT is located at very high altitude. Remember earlier I said you want to go to a high altitude so that you have less atmosphere to look through. We're at about 5,200 meters, which is around 17,000 feet. At this altitude, you have about half of the atmosphere than you have at sea level. So the air is about twice as thin as it is at sea level. You have half the oxygen. You can breathe no problem up here, although it takes a while to get acclimatized, and often people will use oxygen up here. But you can still survive at this altitude. So I'm going to show you now. Oh yeah. One neat thing for those of us in Canada is that this telescope was actually built here in Canada. So the design and construction of the kind of physical telescope was contracted out to a company called Dynamic Structures, which happened to be based in Port Coquitlam, BC, which is near Vancouver. So ACT was actually first set up here in Canada near Vancouver. So here's a picture of it with the Rocky Mountains in the background. I went out a few times to run tests on the telescope. I helped work on the software that commands the telescope motion, where it points. So I was out there working on integrating that back in the 2000s. But Vancouver is really a terrible place to do microwave astronomy. So after it had been kind of engineered, it was shipped, I think literally on the deck of a ship down the Pacific Ocean to northern Chile, where we're actually located. So here's where we're based, in the north of Chile, not too far from the Argentinian and Bolivian border. And we're in the Atacama Desert, which is where the name of the telescope, Atacama Cosmology Telescope, comes from. It's a large desert. It's one of the driest places on Earth. In fact, there are some regions of this desert that have no recorded rainfall, which I find astounding. Like ever since people have started recording weather, there's been no rainfall. That's not in the whole desert. So where we are, it does rain occasionally. I've probably spent 8 or 9 months down in this region when you add it all up, and I've seen it rain once. Um, that being said, on the mountain where we're located, which is here, the mountain is called Cerro Toco. It will snow more frequently. So you do get snow up here occasionally, particularly in the early part of the year in January, February. But apart from that, it's an exceptionally dry place, which is the other thing we want. In addition to being at high altitude, where you have less atmosphere, we want there to be as little water in the atmosphere as possible. And so this is really an ideal place to be. This, by the way, in the background, this is a dormant volcano. It's called Lincancabur. It's the highest peak in the region, and it's just shy of being 6,000 meters. I think it's like 40 or 50 meters shy of 6,000 meters. Okay. So as I mentioned, the telescope was kind of put together, constructed in Vancouver, and then brought down to the site in Chile. So I'm just going to show you some pictures of the telescope going in. Now, this is back in 2007. So here's the foundation being prepared. Here's the telescope coming to the site. I wasn't down here at the time. Someone else on the collaboration took these photos. But you can see it was brought down in 2 parts. So this is the base of the telescope here that's being lowered onto the foundation. And here's the top part of the telescope being driven up, and it was driven up all the way the mountain on the back of a truck. And then the 2 pieces were fit together. And here's a picture of the telescope. This is the telescope here. And this scaffolding that's around it, this is for what we call the ground screen. So this is while the ground screen was being constructed. You can see behind here, there are these white panels. And the panels haven't yet been put in the rest of the scaffolding. But the reason we have this ground screen is because you'll remember I mentioned earlier that everything that has a temperature glows, produces light. And the Earth, the ground, has a temperature and it glows and it produces light that our telescope is sensitive to. And obviously we're not interested in seeing light from the ground. We want to see the light coming from the beginning of the universe. And so what we've done is we've surrounded the whole telescope with this ground screen to shield us from the light being emitted from the ground. So here's some more pictures. This is a good picture of the telescope when only a little bit of the scaffolding has gone up. Here's a picture when almost all the panels have been put in. Here's just to show you some of the infrastructure. So we have generators on site that provide us with the electricity. This is the ditch that the power cables come through. And here's a picture of the completed telescope. This is the picture we have on Wikipedia. And you can't actually see the telescope in this picture. All that you see is the ground screen that's hiding the telescope. But here's a picture looking down from the top of the ground screen where you can actually see the telescope. And we have another ground screen here. around the telescope. And behind it, this is the actual mirror, the primary mirror of the telescope, which is 6 meters in diameter. Now, it doesn't look very shiny. You can also see it if I go back to this picture. You can see the top of the primary mirror here. The whole thing is an oval that follows the shape that I'm tracing with my mouse. It doesn't look very shiny, but that's because it's not shining in optical light, but rather in microwave light. So in microwave light, this is a very good mirror, actually. So just to show you how the light comes into the telescope, here's a drawing. So here's that primary mirror seen from the side, the primary mirror here. So we're looking now at the side of the telescope. So the light comes from the sky, it bounces off of the 6 meter primary mirror. Then we have a secondary mirror here, which is a couple of meters. And then it bounces off of the secondary mirror into the receiver or into the camera of our telescope. Now, I mentioned earlier that the actual structure, all this, the actual telescope itself was contracted out to this company. The receiver, though, which is kind of the heart of the telescope where we actually record the signal that we want to look at, the receiver is built more in-house, largely designed and constructed and put together at some of our universities and research labs. And here's a picture of the receiver or the camera. You'll see, I'll show pictures that show it with people in it, so you'll get a sense of scale, but it's a couple of meters big. And a lot of this is refrigeration. So remember that the CMB today has a temperature of about 3 degrees Kelvin, 3 degrees above absolute zero, or minus 270 degrees centigrade. And so to see this very low temperature, we need our camera to actually be kept at extremely low temperatures. And so we refrigerate our detectors to about 1/10 of a degree above absolute zero. So even colder than 3 degrees Kelvin. And so a lot of this is refrigeration, getting our actual detectors down to this very low temperature. And this is what the actual detectors look like. So shown here on the left, this is my colleague, Laura Newberg. She used to be a scientist here in Toronto, but she's now a professor at Yale University. This is a few years old, so this is an older version of our camera, but just gives you a sense of what one of these things looks like. You certainly can't go to Best Buy and pick one of these things off the shelf, and there's not even like a telescope store where you can go and buy one of these things. We make these things almost completely from scratch in the lab. And this shows you what the pixels of this camera look like. So there's a scale here, and each one of these little holes is one of our pixels. So if you think of your camera, typically we talk about megapixels. So when we think of cameras that use optical light, we use millions of pixels to make an image. But the wavelength, remember, is much longer for microwave light. The wavelength of light we're looking at with ACT is about 2 millimeters, 1.5, 2 millimeters long. And so our pixels have to be a lot bigger. And therefore, we can't fit millions of pixels in our camera. We actually have kilopixels, or thousands of pixels, about 3,000 pixels on ACT. So that's what the actual camera looks like. And here are some pictures. Again, these are a little bit old. I took them about 5 years ago when some of our students on site were closing up the camera, preparing to put it inside the telescope. So this is Patty and Ben and John and Pato from various universities in the US and in Chile. Closing it up to keep it clean. You can see they're wearing gloves here. And here's a picture of the telescope with this very high-tech contraption. I'm being ironic. They're just rolling it out on these kind of makeshift rails that we created on these little wheels here. By the way, you might have noticed that the receiver is very colorful. That's because we had actually a competition. The University of Pennsylvania organized a competition for people to submit artwork to put on our receiver. For the Atacama Cosmology Telescope, the name of the competition was Atacama. And you're seeing here the winning design, which I quite like. I think it's quite beautiful. So here they are rolling the telescope out from the workroom here, or rather they're rolling the receiver out from the workroom here, rolling it towards the telescope so that it can go inside of the telescope and start observing. So that's kind of what the telescope looks like. That's what the receiver looks like. Let me try and give you a bit of a sense what it's like to work down here in Chile. These are our living quarters, which are located at a much lower altitude. The telescope, as I mentioned earlier, is at about 5,200 meters, but that's not a very pleasant place to spend much time because of the thinness of the atmosphere and because of it's often cold up there. So we live, or we reside down at about 2,700 meters, about 5 kilometers from a small town called San Pedro de Atacama, where we can go and get food and where there are plenty of restaurants and so on. But this is a compound here that a small company runs for us and other astronomers, where we can rent office space, where there are some bedrooms, where there's a dining room, and kind of living space. And so this is where we spend our time when we go down to work on the telescope. And today we have a couple people down there full time who manage the operations of the telescope from day to day. And then when we're doing upgrades, or when we need more people down there, scientists from different places in the world, whether it be Chile or North America, will fly down there and spend some time staying here. In addition to our human neighbors in the nearby town, we also have other neighbors. This was a fox that wandered up to our telescope when I was there once. I don't know why it was there, because there's not much to eat up there. But anyways, this was a fox near our telescope. We often see vicuña. These are kind of cousins. They're related to llamas. But vicuñas, unlike llamas, are wild, so they're not domesticated, and they just live in this high plain, high above sea level here. They're very hardy creatures. And then here are some more familiar looking creatures. This is what a traffic jam looks like on our morning commute up to the telescope, a flock of sheep. So the pictures I was showing of the construction was from back in 2007. This telescope is now more than a decade old, and it's been an extremely successful observatory. And over the years, we've upgraded the receiver, we've upgraded the camera that we have inside the telescope. And this is just showing, these are the names of the various receivers that we have inside the telescope. Over the years, we've changed the wavelengths of light that we look at to be sensitive to different things in the CMB. And another really important upgrade we did was back in 2013. We made our camera sensitive to polarization. So the cosmic microwave background, the light is very slightly polarized. That's a property of light that those of you who have studied a little bit of physics will understand. But that turns out to be important, gives us important information about the early universe by looking at the polarization of this CMB light. And so in 2013, we added that capability. And then today, kind of the successor to ACT is going to be the Simons Observatory. So over the next 10 minutes or so, I'm going to finish the talk by showing you some of the scientific results that we've gotten from ACT, and I'll finish by introducing the Simons Observatory, this upcoming observatory. So what I'm showing you here are our most recent results. So these are results that we put out just last month, the most recent maps that ACT has made. And this is a PR image that we created. On the left here are images of the CMB from the Planck satellite that I talked about earlier in the talk. And on the right are images where we've added our data, ACT data, to the existing Planck data. So Planck observed the whole sky. That's what's shown here. Now what's in these maps that I didn't show earlier that was removed in earlier maps is our own Milky Way galaxy. This is the plane of the Milky Way galaxy that goes through the data. And you can see that in microwaves, the Milky Way galaxy is very bright. So when we're looking at the early universe, we normally ignore our own galaxy and we look at other parts of the sky where the Milky Way galaxy isn't present. And on the right, this shows the map from ACT. Now, if you're observing from the ground, you can't see the whole sky. Obviously, you can't see the sky that's on the other side of planet Earth. So from the ground, we can only see about half of the sky, which is what's shown here. The blue regions here are the parts of the sky that we simply can't see from our location on Earth. But here you can see all the parts that we've mapped. You can see the galaxy and the CMB off of the galaxy. And these panels down here in the middle, these are small areas, 4 by 8 degrees of the sky from Planck, and then adding ACT. So this is the overall brightness of the CMB. And in a second, I'll show you larger pictures of this so that you can see the improvement with ACT. But basically, this image is a whole bunch sharper. I'll show that shortly. And then on the bottom, this is what the polarization of the CMB light looks like. There are 2 types of polarized light that we can measure, technically called E and B modes, and I won't get into the details of that, but this is the so-called E mode of the polarization. And here you can really see the improvement that we have with our more sensitive receiver on ACT. On Planck, you can see some of these E mode polarization from the cosmic microwave background, but it is quite noisy. So a lot of this is noise. Whereas with ACT, now you can see that it's nice and sharp on these scales that we're showing here, on these fine scales to which Planck wasn't very sensitive. So let me now show you the overall intensity. Let me show you larger versions of these middle panels, looking at a slightly different part of the sky though. So this is looking at, I think this is about 10 by 6 degrees of the sky. This is the Planck satellite. And now I'm going to flip to what we get when we add our data with ACT. Okay. So I'm going to flip back and forth. I hope that you can, I hope over Zoom that the delay isn't too much and you can see me changing back and forth between these 2 maps. But you'll notice as I change back and forth that you're seeing basically the same patterns, but it gets a lot sharper. It's about 5 times sharper in ACT, and you can see finer detail. And this is one of the real areas where we get a lot of improvement in what we can see with ACT because of this finer detail, about 5 times sharper. Okay. This is important for a couple of reasons. The first thing that we can do with ACT, which sounds a little bit boring, but scientifically is actually super important, is that we can confirm measurements that other people have done with the CMB. And in science, this is really important. You don't want to rely on the measurements that are done just by one experiment or with one observatory, because you never know whether there could be some unknown effect in the instrument that just hasn't been discovered. So you want to make a measurement with multiple different instruments and make sure that you're getting consistent results. And that's something really important that we've done with ACT, is that we've been able to compare the results that we get with Planck and with other experiments to show that what we're seeing is really coming from the early universe, and that the parameters that we're measuring, like the age of the universe, really are accurate. But the other thing we can do is with these sharper maps, is that we can start seeing things that smaller telescopes like Planck aren't as good at looking at. So I'm just going to talk about a couple of those things that I think are really neat that we can do with ACT with these sharper images. One really cool thing we've done with ACT is that we've been able to see an effect that's known as gravitational lensing. I'm not sure if you've heard before, but the path of light as it travels through space can be bent by gravity. If you have a massive enough object, the gravity that it produces can be big enough to actually slightly curve the path of light as it passes by. And that's what this diagram here is showing schematically. So what's shown in the diagram here is a cluster of galaxies. A cluster of galaxies is a group of roughly 50 or 60 galaxies that are all orbiting each other. And all together, if you put all the galaxies together and all the gas between them together, they're the most massive objects in the universe. So here's a galaxy cluster here in this diagram. And all of the light, any of the light coming from behind this galaxy cluster, from other galaxies, for instance, as it passes by this galaxy cluster, the light will get curved. And so that when we see it on Earth, we're seeing light that's been curved. And that's like a lens, right? Just like my glasses are curving the light that's coming through them and sharpening or focusing um, or making the image a little bit bigger. So this galaxy cluster is lensing the light coming from behind it. And all the structure in the universe does the same thing to the cosmic microwave background. So the light from the early universe that we see in the CMB has been traveling for 14 billion years. And as it travels, its path gets slightly bent by all the massive objects in the universe between the beginning of the universe and today. And with ACT, and other experiments have seen this since, but with ACT, we were the first experiment to actually measure this effect, which is important because it allows us to make a measurement of how much mass there is along the line of sight, and that helps us to understand how structure has grown and how the universe has been expanding. So let me just show you what this looks like in the CMB. I'm going to show you not real data, but simulated data. This simulation was made by Alex van Engelen, who also used to be a scientist here in Toronto, but is now a professor at Arizona State. So here's a map of the CMB without any gravitational lensing. And I'm going to flip the slide and it will show you what happens when it gets lensed. So there's the lensed version. It's a very small effect, so I'm going to flip back and forth. And hopefully there's not a big delay with the zoom so that you can see the change in the image. But if you watch closely, you'll see a very small distortion happening. And that's the structure in the universe between us and the CMB deflecting the path of light and causing small changes in the CMB. And because we have sensitivity to the small scales, because we have a very sharp image, we can actually see this effect. Another thing we can see with our sharp images are other objects in the map. So here's another picture. I showed this map earlier, and you probably notice that in our maps we start seeing little dots of light. Some of these are actual galaxies that are very, very bright at microwave frequencies. So some of these galaxies are very dusty, and dust glows very brightly in microwave light. These are galaxies, I'm not sure if these ones in particular, but some of these dusty galaxies will be producing lots and lots of stars in this dusty environment. But what I want to focus on here are these dark spots. These are actually not individual galaxies, but these are those clusters of galaxies that I was telling you about earlier. So we're not seeing the individual galaxies. Even though we have a sharp image, it's not sharp enough to resolve the individual galaxies. But each of these is a cluster of galaxies that has tens, on order 50 or 60 galaxies all orbiting each other. And this is what one of those clusters looks like in visible light. So these white lines here, those are from our maps. This shows in our maps where we see this cluster in microwave. And then this is an image in the background shown here in visible light where you can actually see the individual galaxies in this cluster. Each of these yellow dots is a single galaxy, and all these galaxies are orbiting each other. Right, so in ACT, we're able to actually discover these distant clusters of galaxies. Some of these are billions, even more than 10 billion light years away from the very early universe that we see in our map. And what's shown here, so this is a large map of the sky now. And the gray region here is where we've observed with ACT. And each of these blue crosses is the location of one of these galaxy clusters that we see in our maps with ACT. And so we can see thousands of these galaxy clusters going out billions and billions of years back to when the universe was much, much younger. And what's really exciting is that this is a great way of discovering new clusters of galaxies. So hundreds of these blue crosses of these clusters are brand new discoveries that we've seen for the very first time with ACT. And with the Simons Observatory, we're going to see thousands more of these. And what's neat, and I realize I'm getting out of time, so I'll speed up a little bit here. But what's really neat is that, you know, not only are these really interesting objects astronomically, um, each of these things is interesting in its own right, but what we have now is we have a whole catalog of these galaxy clusters as a function of how far they are away from us, and this gives us a picture of how structure has formed over the history of the universe. And that tells us an awful lot about cosmology, about how the universe was formed and how fast it's grown and so on and so forth. Okay, so let me just spend the last couple of minutes talking about what's next, because we still haven't learned all that we can from this microwave background. We can still learn a lot more. We can discover a lot more of these galaxy clusters. We can we can make our measurement of the age of the universe more precise, but there's still new things that we can do. And I've just listed two of the things that I find most exciting, and that I'll kind of briefly describe here. One thing that we can still do with the CMB is measure the mass of the neutrino, which are those very light particles that I mentioned earlier on in the talk. And since I'm running out of time, I won't say more about this. You can ask me in the questions if you want to know more about this. But the other thing that we still want to do is detect cosmic inflation. And I haven't mentioned this in this diagram yet, but one very popular theory about the early universe is that soon after the Big Bang, within the first second, it's believed that the universe expanded extremely rapidly or that it inflated. And this theory is important because it explains why the gas of hydrogen and helium in the early universe was so smooth, why it wasn't all clumpy. And the explanation is that the universe expanded really rapidly, it inflated, and that smoothed everything out. Right? So it's got a lot of explanatory power, this theory of cosmic inflation, but we don't have kind of extremely convincing evidence of it, right? And the way that we could get evidence is by looking at this polarization, this other mode of polarization. So earlier I mentioned the one mode of polarization that we have measured, this E mode polarization, which tells us many of the same things that the overall intensity tells us about. But this other mode of polarization, these so-called B modes, if there was inflation, would have a very particular pattern implanted upon them. The problem is that it's an extremely, extremely faint pattern, much, much fainter than these patterns, which are already a very, very faint pattern. And so we need much more sensitive measurements in order to see these. Currently, what we've measured, we're not seeing anything from the early universe. All we're seeing is noise from the early universe. And so what we need is more sensitivity. And so there's a lot of effort going on today in order to try and see these B modes to detect cosmic inflation. So so far I've just been showing the ACT telescope, but there are other telescopes that are looking at the CMB from the ground. So at the South Pole, there's the South Pole telescope, very aptly named. This is another large telescope, about 10 meters in diameter, so a bit bigger than ACT. And then BICEP and Keck are smaller telescopes that are really specialized, though, for looking for this polarization pattern that would be a signature of cosmic inflation. SPIDER is a current balloon-borne telescope that flies from the Antarctic. Here's a picture of it going up a few years ago. And then near us, we actually have a couple of neighbors on Cerro Toco in Chile. So this is ACT. But near to us, we also have the Simons array, and then CLASS. And these experiments are also looking at the CMB and are also looking for this primordial signal from cosmic inflation. And so just in the last couple of minutes, I'm going to talk about kind of the next generation of telescopes, which is the Simons Observatory. And so Simons came about when the members of the ACT collaboration decided to team with many of the members, or with the members of the Simons array, to create a brand new observatory called the Simons Observatory, which isn't to be confused with the Simons array. It gets its name from the Simons Foundation, the Heising-Simons Foundation, which have provided a large portion of the funding for these. This is Jim Simons, after which these foundations are named, who is extremely interested in the science we're doing. He's a mathematics PhD, but he has a keen interest in science. And this is now a very large collaboration that includes some of us from the U of T and these other institutions shown here. And so the plan is to build even more telescopes near ACT and these other telescopes here. So this is kind of the current nominal location for these new telescopes. And we're going to start by building 4 new telescopes. One is going to be another big telescope that's similar in size to ACT, but what's special about this telescope is we can put a much bigger camera inside of it. What currently limits us on ACT is that we don't have any more space for a bigger receiver. And this is the picture of the receiver that's currently under development. This is from the University of Pennsylvania, and it's much bigger. ACT, is kind of this size, a couple of meters tall, but this receiver here, you can, when it's empty, when this shell is empty, you can easily fit several grown adults inside. And this means that we can put tons more detectors. So we're moving from having a few thousand detectors to having tens of thousand detectors. And then in addition to the large aperture telescope, we're going to build 3 small telescopes, and these are going to help us to be sensitive to that polarization signal that will tell us about inflation. And the reason we have 3 is so that we can have as many detectors as possible. So put together, we'll have 30,000 detectors in these 3 small telescopes. You add them all up, and we're going to have many tens of thousands of detectors all working together, all measuring the microwave background. And we're going to be able to do really amazing science with the Simons Observatory. We're going to be looking at the origin of the universe. Did the universe inflate in its first few instances? How massive are neutrinos, these fundamental particles? And then a number of other really interesting science questions, including, and I find this really intriguing, some astronomers believe that there's another planet in our solar system, which is dubbed Planet 9. Because of the shape of some of the other planets, it's inferred that perhaps there's another planet that no one's been able to see yet. And it's possible that because we're observing so much of the sky, it's possible that if there is another planet, that it would show up in our maps, which would be kind of cool. So that we have a telescope that is built for studying these kind of really big picture questions about the universe and its history, but that can do all kinds of other really, really interesting and important science. So I'll finish there. I'll leave this slide up as we move to questions. What I've got here are, if you're interested in learning more about the CMB, I've got here 3 books that were recently published by some of my colleagues on ACT and Simons. These are aimed at a general audience. They're not science textbooks. And then here are the websites of the 2 observatories I've talked about. And then here is a short documentary that's available online about the Simons Observatory if you're interested in learning more about science. But I'll finish there. Thanks for watching. Thanks for tuning in. Thanks to those of you who will be watching this recording later. Sorry for running a little bit over, but I'd be more than happy. I'm very available to answer any questions that people have. And I know too that the ASX Society at the end has an advertisement, and that there's a final slide for that when they're ready. Thank you.
Thank you, Professor Hincks, very much for that fascinating insight into the history of the universe. It really is incredible what lies just beyond the normal human perception. So for everyone, we definitely have some time for some questions. Please ask away in the chat. Give them a minute or 2 to type anything up.
And if there are no questions, that's fine too.
I would ask something if you have a minute.
Yeah, please.
A couple slides ago, you mentioned that these observations could help us mass neutrinos, and you said you could elaborate on it a bit later. Do you mind elaborating? Right, thank you.
Sure. So neutrinos, I don't have any good slides about neutrinos, but neutrinos are extremely light particles that have been detected. They're produced, many of them, billions and billions, are produced every second inside the sun. And right now, they interact very weakly with other type of matter. So, but right now there are billions of neutrinos passing through your head that are coming from the sun. So they're extremely numerous, but they're very, very light. Um, and of all the elementary particles, we know the mass of the proton, we know the mass of the electron, we know the mass of the neutron, but the one thing we don't know the mass of are the neutrinos, because they are so light and because they interact so weakly with other particles. But let me just go back to that pie chart that I was showing earlier. They're very light, but they do form an appreciable fraction of the mass of the universe. And in fact, in the early universe, they had a much larger proportion of the mass of the universe. And what that means is that they do have a measurable effect on how fast structure grows. The more massive they are, the more effect they have on how galaxies and groups of galaxies evolve. And so by looking at those clusters of galaxies, at looking at the gravitational lensing, which depends on the mass of the structures that we're seeing, it turns out that you can actually constrain the mass of the neutrino particle. And with Simons, if I can just slip briefly into a technical term, depending on the hierarchy of the three neutrino species, we'll either be able to we'll probably be able to make a 2 or 3 sigma, a very weak measurement, or if it's an inverted hierarchy, then we could even make an actual measurement. Maybe not a very significant measurement, but an interesting and scientifically useful measurement. I'm not sure if you want me to clarify any of that, or if that was a good start.
Oh, that was really fascinating, Professor. Thank you. Thank you for the
You're welcome.
explanation. There is one question in the chat there. Perfect. Professor, how do we find the compositions of the universe with the CMB?
Right. So presumably, how do we know that 5% of the universe is made up of atomic matter, and 25% is dark matter, and 70% is dark energy? Well, it's kind of hard to explain in general terms. The explanation is technical, but what I would say is that the precise shape of that pattern in the microwave background depends on how sound waves propagate through it. So if you think about sound waves propagate in different ways in different mediums. So if you think about for example, air, the speed of sound is different in air than it is in water. And the speed of sound, even in air, depends on what the temperature of the air is. And if you look at the precise shape of the waves that travel through a medium, it depends on what the medium is made out of. And kind of analogously, the precise shape of the waves, which creates that pattern that we measure on the CMB, depends on what it's made out of. So by looking in detail at the shape of that pattern, we can tease out the composition of the universe. And there are a couple of other factors that go into that, like the size of that pattern that I was showing earlier. But that might be how I would start to explain it. I hope that gives a bit of a better picture.
Thank you very much. There's 2 more questions, actually. Let's go off of the more similar one to your previous response. How does the CMB help to determine the geometry of space-time during the initial phase of the universe?
Right. So the initial phase of the universe, correct me in the chat if I'm not answering the question you're asking, but if you mean by initial state of the universe, like the very first instance after the Big Bang, here, the main question, so we understand how the universe expands starting well within the first second after the Big Bang. We understand very well how fast it expands and how matter and energy behaves. We have good theoretical models that match the data and match many different kinds of data, not only the CMB. What we don't really understand is what happened in the very few instants after the Big Bang, particularly this period of cosmic inflation. Now, I should point out that this diagram, time isn't divided up evenly from here to here. So you'll notice that this is 10 to the minus 32 seconds. So here on the diagram is still within the first second. And then we jump all the way to 300,000 years. So the time isn't progressing evenly along this axis. So the real question is, what happened in these first instants? Why is the universe so well behaved? Why is the universe so smooth? Like when we look at the CMB, it's the same brightness everywhere, which means that the universe was extremely smooth and homogeneous early on. And the best explanation we have for that currently is that it stretched out really fast early on. But that's about it. Like there's some theoretical models for how that happened, but we don't have any kind of, beyond the smoothness, we don't really have any firm and compelling evidence that that's actually what happened. And so it turns out that that inflation would have produced gravity waves. You might have heard of gravity waves when LIGO a couple of years ago announced their big result when they saw two black holes spiraling in, which created gravity waves, which are ripples in space itself. And those gravity waves, if they were created by inflation, leave a very distinctive pattern in the polarization of the light. They leave kind of a swirling pattern in what we call the B modes. Where was it? Yeah, the B modes, which no one has measured yet, if they're there. So what we're looking for are the imprints of the gravity waves that would have been created when space was being inflated really rapidly for the first second after the Big Bang. So I've answered what I think was the question. I hope I answered the question, or at least addressed the question.
Thank you again, Professor. If anyone does need a clarification, feel free to clear that up in the chat. And one more question in the meantime. Someone's wondering why the observatories have to be at a very low temperature to observe the CMB.
Yeah, that's a really good question. So let me go back to a picture of our camera. So remember I mentioned at the beginning of the talk that in the early universe, this gas was really hot, about 3,000 degrees. But because space has expanded, the wavelength has stretched, and so now the temperature, it's as though the temperature we're looking at is really cold. So the light that we see in the microwave background corresponds, it's like looking at an object that's about 3 degrees above absolute zero, or about minus 270 degrees Celsius. So the signal, the signal we're looking at has a very low temperature. And therefore, if we want to see it, we need our camera to be even colder. If your camera is warmer than that, the temperature of your camera produces a whole bunch of noise. Your camera would be glowing at temperatures that's even hotter than the signal you're trying to look at. And so in order to actually see the CMB, we need our camera to be at an even lower temperature. And so it's, many, many times colder than the actual CMB. So this is an interesting fact. Space isn't at absolute zero. The temperature of space is about 3 degrees Kelvin, because that's the temperature of the CMB.
And that is just really incredible, Professor. Thank you for clearing that up.
Yeah, it's amazing that we get these. So I mentioned that we have generators on site. A lot of the power that we use on site is actually refrigeration. It takes a lot of electricity actually to cool down our detectors that much.
Well, it's really interesting to know. If that's all the questions, any last minute thoughts? Anybody in the audience? Okay, I think that might, oh, one more, perfect. Let's see. As you also talked about detecting the gravitational waves during or at the same time that CMB, do we of know about any initiatives that are going to measure gravitational waves?
That's a really good question. So um, I might kind of reframe the question to ask, well, why not look for the gravitational waves themselves? Why are we looking for the imprint they make on this very old light and measuring that instead of looking for the waves themselves? And the answer to that is that today, so those waves, if they were made, would exist still today. So they would be imprinted on space today, but they're extremely, extremely, extremely small. Now, as I mentioned earlier, um, people have actually seen gravity waves, not produced in the early universe, but produced by very energetic systems. So for instance, if you have two neutron stars or a neutron star and a black hole, or two black holes that are orbiting each other, as they orbit, they slowly fall in and they spiral faster and faster until they merge together. When that happens, they produce a lot of gravity waves. And those gravity waves are large enough that they actually have been detected. And that was a huge discovery a few years ago. I can't remember the exact date. I think it was in 2017. And the name of the experiment was LIGO. And those experiments were actually measuring waves in space that came from that kind of event. And so, in principle, you might hope to see a background of gravity waves that's produced from the very early universe. But that's now far smaller than our current technology. And so today, the best way to see those gravity waves is through their effect on the CMB. If in fact there was inflation, if we don't see these gravity waves in our maps, that's also very interesting, because it means that most of the models that people have for inflation simply don't work. You might be able to construct other models that produce much, much smaller gravity waves that we can't see, in which case we're out of luck. But as always in science, not seeing something, while it might not make headlines as readily, can actually be just as valuable scientifically.
And that's an excellent moral to end off on, Professor.
Thank you.
Thank you. And could you kindly go to the last slide, please?
Sure.
Right, thank you very much. And thank you to everyone in the audience who stuck around. We have one final surprise announcement for all of you. This October, ASX is very happy to be co-hosting the Toronto branch of the International Space Apps Challenge. So Space Apps is the world's largest hackathon and is annually organized by NASA with the help of worldwide local affiliates. Participating teams spend a weekend tackling some of the world's most interesting space-based problems, and up here in the Great White North, teams benefit from the additional support of the Canadian Space Agency. For Space Apps Toronto 2020, ASX is collaborating with the National Students for the Exploration and Development of Space, as well as RU Hacks over at Ryerson University to bring you the very best in online-only, physically distant space innovation possible. Registration opens on Friday, and be sure to check out those social media links for some more info. Also, feel free to ping us on any of our social media platforms and or email us for any other questions you have about this. So thank you very much again to Professor Hincks for that amazing presentation and Q&A period. That is really eye-opening. And ASX hopes everyone here has a safe and pleasant remainder of their summer. We look forward to seeing all of you at our first events in September. Thanks all of you for attending.